Math 161, review of Unit 1. Starting out just mentioning the formulas that we'll be working with. We're working with lines, straight lines, ellipses, hyperbolas, parabolas, and in order to identify the features of these shapes, we want to put them in a standard form. For the straight lines, the most general form for a straight line is ax plus by plus c equals 0. X and y are variables. The a, b, and c are constants. So this is the thing to note about here is x and y are both to the first power. So the slope of a line, if you have 2 points, you can compute the slope of the line. The difference of the y values divided by the difference of the x values. So it's y2 minus y1 over x2 minus x1. And then once you have the slope, you can write an equation for the line using the point slope form. Y minus y1 is equal to m times the quantity x minus x1. And I'll go over some specific examples that will make this more clear. If you simplify this and solve for y, you get the slope-intercept form, which is y equal mx plus b, or sometimes it's written y equal b plus mx. Particularly statisticians often put the intercept first. Okay, so a couple of comments. The slope-intercept form can also be expressed using function notation. If you just have one formula for y, like we do here, then that means y is a function of x. And so sometimes expressed as instead of y equal mx plus b, f of x is equal to mx plus b. In this context, f of x does not represent multiplication, but it just emphasizes that y is a function of x. And we'll go in more detail into functions after the exam. The rest of the course after this exam will be mostly about functions. And all lines can be written in the form ax plus by plus c equals 0. But vertical lines cannot be expressed in that form. For vertical lines, b is equal to 0. And such lines have no slope, no point slope form, no slope intercept form. And they are not functions of x. Okay, so I'll go over some of the other formulas, and then we'll get into some specific examples. The other formulas are all under the category of conic sections, because they're can be represented as the intersection of a plane and a cone, and they are ellipses, hyperbolas, and parabolas. So conic sections are a degree 2 equation. For the straight lines, we had a degree 1 equation here. Highest power of x and highest power of y are 1, but here we have the highest power of x and the highest power of y are 2. So these are degree 2 equations, and we have some formulas for those also. I'll get into more detail. I think it's a little more clear if I do it in the context of a specific example. So the first example, we're given 2 points, and we want the equation of the line through those 2 points. There's only one way to draw a straight line through 2 points. So if you have 2 points, that tells you everything you need to know about the line. So you can compute the slope, and so we can label these points x1, y1, and x2, y2. And then the slope is going to be y2 minus y1 over x2 minus x1. So it's in this case 3 minus 1.5 divided by 4 minus 1. Okay, so it's 1.5 divided by 3. That comes up to be 0.5, or you could express it as a fraction 1/2. So the slope is 0.5 or 1/2, and now we can write down the point slope form. y minus y1, y minus 1 equals 0.5 parentheses x minus y minus 1.5 rather equals 0.5 times x minus 1. So it's y minus y1 equals 0.5 x minus x1. And then, so that's the point slope form. This point slope form is not unique. We could have used the other point, or actually we could have used any point on the line, and we'll get a point slope form. But if you simplify it, you'll get the there's basically only one slope intercept form. So in step 3, if we simplify this and solve for y, we can distribute the 0.5, and that'll give us y minus 1.5 equals 0.5x minus 0.5, and then if we add 1.5 to both sides of the equal sign, that'll give us y is equal to 0.5x plus 1. So that's the slope-intercept form. They call it the slope-intercept form because you, looking at this equation, you can see the slope and you can see the y-intercept. Okay, so you can also estimate the y-intercept from the graph. It looks like the y-intercept is where the line crosses the graph, so it looks like it's about 1. And we can also write this in function notation. We just have one formula for y, so that means y is a function of x. And we can write this as f of x equal 0.5 x plus 1. Okay, so that's an example of using the equation for a straight line. The next example, example B, this is a degree 2 equation, so it's not going to be a straight line. We have an x squared and a y squared. So let's pull back that formula sheet again that I kind of skipped over. So we have something that's more or less in this form here, general form for a conic section. You notice for ellipses, the x squared term and the y squared term have the same sign. And that ellipses include circles. If a and b is a is equal to b, then it'll be a circle. Hyperbolas, the x squared term and the y squared term have opposite signs. Parabola, either you have an x squared without a y squared, or you have a y squared but no x squared. So so it looks like it's going to be an ellipse, and it might be. Sometimes it could be you get an equation that you can't put in this form. Maybe you try to put in this form, you get equals -1 instead of equals 1, and in that case it would be what's called a degenerate conic section. It could be a single point or no solution, but our best guess now is that it's going to be an ellipse. We're going to try to put it in the form for an ellipse, and so we want to put x with x and y with y. So I'll rewrite this 9x squared minus 72x plus 4y squared minus 8y equals -112. And now we want to factor the leading coefficient of each variable. So in front of the x squared, we have a 9. We want to factor that out. So 9 parentheses x squared minus 8x. And in front of the y squared, we have a 4. I'm going to factor that out. 4 parentheses y squared minus 8y equals -112. And now we want to take half the coefficient of x. Half of 8 is 4, and square that. Half of 8 is 4. 4 squared is 16. And take half the coefficient of y. Yeah, I forgot to divide. 8 divided by 4 is 2. There should be a 2 here. Half of 2 is 1. 1 squared is 1. 1 squared equals 1. Okay, so so that's what we want to add to both sides of the equal sign. We want to add the 16 and the 1 to both sides of the equal sign in order to make these into perfect squares. So this will give us the right smaller here, 9 parentheses x squared minus 8x plus 16. Oh, I think I'm frozen here. Okay, I froze there. So it's 9 parentheses x squared minus 8x plus 16. And then I want to add the, I know I kind of froze there. So what I did before was take the half the coefficient of x and squared that, half the coefficient of y, squared that. That's what we want to add to both sides of the equal sign. So I want to add 1 to both sides of the equal sign here. So it'll be plus 4 parentheses y squared minus 2y plus 1 equals negative 112. And then I have to do it to both sides. So the 16 I added was inside parentheses with a 9 on the outside. So I'll add plus 9 times 16. And the 1 was inside parentheses with a 4 on the outside plus 4 times 1. Okay. Okay, so now we can factor these. This is x minus 4 times x minus 4 here. 9, x minus 4, x minus 4. Now they're perfect squares. Plus 4, y minus 2 times y minus, y minus 1 times y minus 1. There you want, so x times x is x squared. You need two numbers to multiply to 16, add up to negative 8. So negative 4 times negative 4. And likewise with the y, y times y is y squared. You want two numbers to multiply to 1, add up to negative 2. So negative 1 times negative 1. This side here, 9 times 16 is 144, plus 4 is 148, minus 112 would be 36. So that's so now it's starting to look like the standard form for an ellipse. We can write the factors in exponent form here. This is 9 parentheses x minus 4 quantity squared plus 4 y minus 1 quantity squared equals 36. And the standard form has an equals 1. It's starting to look like the standard form, but the standard form for an ellipse has an equals 1. We have an equals 36. So what we want to do is divide each term by 36. Then 9 and 36 goes 4. So we'll have x minus 4 quantity squared over 4 plus 4 and 36 goes 9. Y minus 1 quantity squared over 9 equals 1. And that's pretty close to standard form. Oftentimes the text will stop there. To exactly match it in standard form, we instead of just a number, we want a number squared on the bottom here. Standard form for ellipse has an a squared and a b squared. We can we'll take this a step further, and but you can stop there if you want. Take it a step further and write this as x minus 4 quantity squared over 2 squared plus y minus 1 quantity squared over 3 squared equals 1. So now we can identify the features of the graph. So this is the number inside parentheses with x. I'm calling that h. I think our text puts, I like to always put h with x just so we don't have, so the formula is always the same, but and y with k. I like to put a with x. In the text, sometimes they put a to be whichever number is bigger. but I like to always put A with X so the formula stays the same each time, and B with Y. So now it's in the standard form for an ellipse. So this is in the form x minus h squared over a squared plus y minus k squared over b squared equals 1. So the center is going to be hk, which is 4, 1, 4 comma 1. And if we go down b and up, b is a 3, so we go down 3 and up 3 from the center, we get the vertices, and if we go so it's basically adding 3 and subtracting 3 from the y coordinate here, 4 comma minus 2, 4, and if we go left and right, 2, the a radius, the x radius is 2, the y radius is 3. So we go left and right 2 from the center. So now we're adding, subtracting from the x coordinate. We get 2, 1. And that's maybe a little bit clearer on the graph. You can actually do that on the graph. Let me actually make the graph. So we have basically enough information to make a pretty good graph here. Okay, so the center is at 4, 1, 4 to the right, up 1. And then I'm putting that in black because the center is not actually part of the, that doesn't satisfy the equation. The center is a feature of the ellipse, but it doesn't really satisfy the equation. So I put the parts that satisfy the equation, I'll make those in red. So from the center, we want to, let me just rewrite the equation on the same page. So we're, so we have x minus 4 squared over 2 squared plus y minus 1 squared over 3 squared equals 1. So the center, hk for 1, and the a is 2, b is 3. So the radius in the y direction is 3. From the center you go up 3, so that's this point here, and you go down 3. So 1, 2, 3. It's about right here. I made the scale by hand, so I think it's actually a little bit uneven here. So it's going to look a little bit out of kilter, but from the center, the x radius is 2, so we want to go 2 to the right and 2 to the left. And then, so those are the co-vertices. So then if we connect the dots, that'll give us our ellipse. Okay. Okay, so so that's basically the ellipse. Sometimes they might ask for the minor and major axis. So the minor axis connects the two co-vertices. That's the shorter axis. The major axis connects the vertices. I'm drawing those in black because they don't satisfy the equation. What's in red is the points that satisfy the equation. And then the foci, to get the foci, you need to compute C, which is C is equal to square root absolute value of a squared minus b squared, square root absolute value 2 squared minus 3 squared. Okay, so this is 2 squared is 4, 3 squared is 9. So it's square root of absolute value of 4 minus 9. 4 minus 9 is negative 5. Absolute value of negative 5 is 5. So it's a square root of 5. You could do a trial and error. It's 2 squared is 4. 3 squared is 9. It's going to be approximately 2.2. You can do a trial and error there on that. So it's the foci are located along the major axis. So from the major axis, we want to go up 2.2 and down 2.2. Down a little bit more than 2. So those are the foci. So this is a focus here. So it's the x-coordinate is going to be the same as the center. So it's 4 comma, and then we're adding root 5 to the y-coordinate. So this one is 1 plus root 5. The other focus down here would be 1 minus 4 comma 1 minus root 5. It's I'm trying not to I would write that in here, except the graph is already sort of crowded here. It becomes kind of hard to read if I write too much on top of the graph. Okay, so that's basically that's the ellipse. Okay, so let's go over another example. Here's another conic section. In this equation, x squared and y squared have opposite signs. So it's probably going to be a hyperbola. So here's we have two formulas for the hyperbola, depending on the x squared could come before the minus sign, or the y squared could become before the minus sign. It'll be a hyperbola, and this is yeah. If the y squared if the x squared comes first, it's going to open left and right. If the y squared comes first, it'll open up and down. It could be if you try to put this form and you get equals 0, then it's going to be a pair of straight lines. And that's another example of a degenerate conic section. But most of the time, most of the examples it'll come out to be a hyperbola. So anyway, we want to try to put it in this form here, and then in order to identify the features. So again, we want to put x with x and y with y. So I'll rewrite this as x squared minus 4x minus 4y squared minus 12y equals 9. You have to be careful with the signs. Sometimes it's easy to make a mistake with the signs here. We want to factor the leading coefficients of x squared and y squared. So we'll have 1 parentheses x squared minus 4x, and then we have a negative 4, and it'll be y squared plus 12y. So you have to be a little bit careful about that. That's negative 12 divided by negative 4 is a positive 3 plus 3y. Now we can complete the square. And so I'll rewrite this as 1 parentheses x squared minus 4x. Half of 4 is 2. 2 squared is 4. So I want to add 4 here. And y squared plus 3y. Half of 3 is 3 halves. 3 halves squared is 9 fourths. Add 9 fourths here equals 9. And then whatever we added over here, we also have to add on the right side of the equal sign. So the 4 was inside parentheses with a 1, so we'll add plus 1 times 4. And the 9 fourths was inside parentheses with a negative 4 on the outside, so we'll add a negative 4 times 9 fourths. And that's going to be negative 9, so those will cancel. You have a positive 9 and negative 9, so we'll just have 4 on there, on that side. Okay, so let's factor these. 1 parentheses, x times x gives us x squared. And then we need two numbers to multiply to 4, add up to negative 4, so it'll be negative 2 and negative 2. And we'll have minus 4 parentheses. Y times y is y squared. And then we need two numbers to multiply to 9 fourths, add up to 3. So it'll be plus 3 halves. Equals 4. Okay, okay, so we can write this now in exponent form. This will be 1 parentheses x minus 2 quantity squared minus 4 parentheses y plus 3 halves quantity squared equals 4. Okay, so we have an equals 4 here. We want an equals 1. Let me look at the standard form again. We want an equals 1, so we have an equals 4. So we want to divide each term by 4 to get the desired form. And that'll give us x minus 2 quantity squared over 4 minus y plus 3 halves quantity squared over 1 is equal to 1. So now it's in the standard form, and a lot of times the book will leave it like this because it's close enough to the standard form to identify the features. But the standard form, on the bottom, instead of a number, we have a number squared. Also, inside parentheses, instead of a plus sign here, we have a minus sign there. So if you want to exactly match it to standard form, you can write 4 as 2 squared, and adding 3 halves is the same as subtracting negative 3 halves. Write 1 as 1 squared, and now it's in the form that we can identify the features. So h is 2. This is going to be hyperbola. H is 2, k is negative 3 halves, a is 2, and b is 1. Okay. So the center is 2 comma negative 3 halves. That's hk. And then so let's and the slopes are okay. So let's plot the let's start the graph here. So the center is down. I'm just drawing a coordinate system here. Okay, so the center is 2 to the right, down 1.5, 3 halves or 1.5. So that's the center. I'm going to put that in black. So that's the center. So step 11, I say plot the center. So that's the center. And the vertices, because the x squared comes before the minus sign, the vertices are going to be A away from the center. Yeah, if the y squared was before the minus sign, then we go up and down B from the center. But A is before the minus sign, so we go left and right 2. A equals 2 from the center. And those are the vertices. Okay, so let me plot those. We want to go 2 to the right and 2 to the left from the center. Okay, and then we need, sometimes you could compute the co-vertices. They're not really, I don't really usually use those, but in case you see them referred in the book, the co-vertices, because the y comes after the minus sign, we're going to use those for the co-vertices, and they're not actually part of the hyperbola, but you want to go up 1 and down 1 if you want. You can plot those. Those are the co-vertices from the center. Okay, so then we want to compute the slope of the asymptotes. So the slope of the asymptote is plus or minus b over a. In this case, it's plus or minus 1 over 2, or it's the rise over the run. From the center, if we go over 2, we want to go up 1 from the center. Every time we go over 2, you go up 1. So here, from the center, go over 2, up 1, and we have a point there, and we can draw an asymptote through that point. If we go in the other direction, you go over 2, down 1. Okay, and then the other asymptote, if you go 2 to the right, down 1 from the center, we get another point here. And we could also go 2 to the left, up 1, okay, so those are the asymptotes, and then we want to from the vertices, we want to extend the graph toward the asymptotes. So it'll be something like this. Okay, so there's the hyperbola. We can also compute the focus. For some applications, it's important to know the focus. So for the focus, it's the square root of a squared plus b squared. In this case, the square root of 2 squared plus 1 squared, square root of 5. Square root of 4 is 2. By trial and error, we can estimate about 2.2. So if you go from the center along the transverse axis, this is the transverse axis here. If you connect the two vertices, that's the transverse axis. You go 2.2 to the right and 2.2 to the left. those would be the two foci. So this is the coordinates here. We're actually doing, it's approximately 2.2, but it's root 5. So it'd be 2 minus root 5, comma, negative 3 halves. And the other one is going to be the same. It's going to be 2 plus root 5, comma 3 halves. I don't want to write too much on the graph here because it's getting kind of crowded, and if I write too much, it's going to be hard to read the graph. But the coordinates of the two foci are 2 minus root 5, comma negative 3 halves, 2 plus root 5, comma negative 3 halves. If you connect the two co-vertices, that's called the conjugate axis. So that's this is the conjugate axis here. Connect the two co-vertices. Okay, so that's a hyperbola. Now, if y had come before the minus sign, these co-vertices would actually be the vertices, and then our hyperbola would go something like this here. It would be open up and down instead of left and right. Okay, so next example, this equation here, we have a y squared but no x squared, so this is going to be a parabola. If only one of the letters is squared, it's a parabola. This parabola is going to open left or right because you have the y squared. If you have an x squared but no y squared, then the parabola opens up and down. So we want to try to match it to this form here, because we have the y squared, y minus k quantity squared equals 4 times p times quantity x minus h. And that will help us to identify the features of the parabola. So to get it in that form, we want to subtract y from both sides so that we have both the y terms on the left side. So there will be, we'll have y squared minus 6y equals 2x minus 13. And then we want to complete the square. So half of 6 is 3, 3 squared is 9. So we make this imperfect square by adding 9. And then if we add 9 to the left side of the equal sign, we have to add 9 to the right side. Okay. And then we can factor the left side. Y times y gives us y squared. We need two numbers multiplied 9, add up to negative 6. That's negative 3 and negative 3. Equals 2x, negative 13 plus 9 is negative 4. And we can write this in exponent form. Y minus 3 quantity squared equals 2 parentheses x minus 4. Okay, so now it's starting to look like the form we want. In order, instead of a 2 here, we want a 4 times p. So if we multiply 4 times 1/4, that'll give us what we want here. So I'm going to rewrite this as y minus 3 y squared equals 4 times 1/4 times 2 x minus 4. Well, this part here is 2/4, which reduces to 1/2. So we'll have y minus 3 y squared equals 4 times 2/4 x minus 4, or it reduces to 1/2. So we'll have y minus 3 quantity squared equals 4 times 1/2 times x minus 4. So okay, so that enables us to identify the features of the parabola. So we have k is 3, h is 4, and p is 1/2. Okay, and sometimes the book doesn't always take it all the way to this step here, but if you want to exactly match the form, then you it would take it take it to this point here. Oh, you know what? Something's not right here. Yeah, this is when I factored this. I keep making the same mistake here. If I need to factor out the 2 here, so that's x minus 2 quantity squared, or x minus 2 rather, quantity x minus 2. Okay, so the vertex of the parabola is going to be at 2, 2, 3. See if I have that already written down here. The vertex is HK, which is 2, 3, and the focus, to get the focus, you want to add 1/2 to the y coordinate. So the focus is going to be 2, 3, and actually I'm going to add the focus to the x coordinate rather, 2.5, 3, or 5 halves, 3. So we want to add the focus to the x coordinate. Okay, so let's do that on the graph. Make a graph here. So this is going to be okay, so the vertex is at 2, 3, 2 to the right up 3, and the focus is 2.5 to right up 3, and we can get 2 additional points on the parabola if we go 2 times p is 2 times p would be 2 times 1/2 equals 1. Go up and down 1 from the focus. And that'll give us 2 additional points. So if we go up 1 and down 1, we get 2 additional points. And then we can connect the dots and extend it to the extend it out. See if I something like this. Okay, so that's our parabola, and this point here is the focus. That's 5 halves, 3, and this other point is the vertex. There's a line of symmetry goes through the focus and the vertex. This is this line here is the line of symmetry. And then if we go p to the left from the vertex, we get the directrix. This is the directrix. Okay, so that's for some of the applications. The directrix is important, and the line of symmetry is often useful in applications. It kind of makes it. If you have later in the course when we have parabolas opening up and down, it's sometimes convenient to locate the vertex as halfway between the two intercepts. It's another way of locating the vertex. Okay, so I think that pretty much covers this topic. So that concludes this presentation.